Okay, so we're going over the practice exam 1 for Chem 113, Organic Chemistry 2. So let's start going through the questions and providing our responses. So in question 1, we're asked, which of the following compounds has a faster rate of E2 elimination? Draw the structure of each product in an MO diagram. And we know one compound reacts to yield a single enantiomer. Circle the compound and provide a mechanism, and clearly indicate the product stereochemistry. Okay. So we have two substrates, so let's draw the mechanism for each of these substrates. So in this first case, we have a cyclooctatriene substrate. And for an E2 reaction, the elimination is anti-periplanar. And if we make an MO diagram, so drawing out a frost circle, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That gives us the template for our MO diagram. So we have our bonding, our anti-bonding, and our non-bonding. We have 8 pi electrons. That follows the 2n rule. So we can conclude cyclooctatetrene is anti-aromatic. And since we have 8 pi electrons, if we fill in our MO diagram, we see that we have a half-filled highest occupied molecular orbital. And as a result, this is a very unstable compound. And we would conclude from this MO diagram that cyclooctatetrene is anti-aromatic. Does that logic make sense to everyone? Now, in contrast, if we take a look at this cyclohexadiene structure, we notice that upon elimination, we are able to generate benzene, which we all know is aromatic, but I want you to actually justify your answer. Memorization is no substitute for a justification. Okay, so we make our frost circle. We know we have 6 pi electrons, which corresponds to the 2n plus 2 rule. So we can conclude that benzene is aromatic. 1, 2, 3, 4, 5, 6. So we have a completely full highest occupied molecular orbital, and we filled all of our bonding molecular orbitals. So we can conclude then that benzene is aromatic. Okay, now why is this important? Well, in general, if you're generating an anti-aromatic product, so if we think about our energy diagram for a moment, if we're generating an anti-aromatic product, our product will be relatively unstable, right? And because during elimination, your transition state resembles your product alkene, the higher energy your product, the greater the activation barrier for this elimination. So we would expect elimination to yield an anti-aromatic system to be slow. Does that argument make sense to everyone? Does that idea make sense? In contrast, if we're making an aromatic system, elimination is fast. In fact, you may not even need base. I'd want the 1 to 3 sentence explanation. I'm providing it verbally, just so that way, just because it works better with the recording system. Essentially, elimination to form an anti-aromatic product is disfavored, has a greater activation barrier because the transition state resembles the product, which is higher in energy. Does that answer your question? So we've addressed the first 2 points. So one compound reacts to yield a single enantiomer. Well, so it's something other than elimination. Circle the compound and provide a mechanism. Now, this cyclooctatriene substrate really doesn't want to engage in elimination. It would rather do anything else rather than engage in elimination. So what reaction would give us an enantiomeric product? Besides elimination, what other reaction pathways are possible? SN2, exactly right. So this is one of the rare cases where tert butoxide is more than capable of participating in an SN2 reaction. And that in turn generates a single enantiomeric product. So this is a case where SN2 is favored even for an allylic substrate. Sure. I mean, the energy diagram for the second compound would look something like this, with a smaller activation barrier. Does that answer your question? Okay, so we fully answered this example. Any questions on question 1?
Would you write for that final mechanism plus enantiomer since you're trying to show the enantiomer?
In this case, no, because I drew these products as a single enantiomer.
Oh, okay.
Because the reactants are drawn as single enantiomers, if you're dealing with an SN2 reaction, which is stereospecific, you'd only get one product, one enantiomeric product.
Oh, okay.
Right, because the SN2 occurs with inversion.
Right, okay, makes sense.
Perfect. Any other questions on this example? Okay, so let's look. No, it's not racemic. It's a single product, single enantiomeric product. Because the SN2 occurs with inversion, right? So if you start with one enantiomer, you'd get another single enantiomer with the opposite configuration at that center. Does that answer your question? Perfect. Okay. So let's look at this next example and let's try to predict the products from each reaction and draw a mechanism. So in this case, we have a carboxylic acid, which is a pi acceptor, and we have an alcohol, which is a pi donor. The pi acceptor directs to the meta position relative to the carboxylic acid. The pi donor is orthopara. Obviously, we don't see para direction because the substituent's present at that position. Okay, so we have nitric acid. And to showcase this reaction, our first step is to generate our electrophile, which is the nitrinium ion. So for our first step, we're going to protonate we're going to protonate nitric acid with sulfuric acid. From there, we now have an activated leaving group in the form of water, and we can kick out water and generate the nitrinium ion. Perfect. Now we can get the aromatic ring involved in this mechanism. Now that we have our active electrophile, our aromatic ring is going to attack our electrophilic nitrinium ion. Note that our carbocation is stabilized by our pi donor group. And then for our next step, water will facilitate elimination and regenerate our aromatic ring. So this gives us the following single product. Does this first example make sense? Okay, let's keep going then. So in this case, we have an SO3H group, which is an electron withdrawing group. And we're trying to perform a Friedel-Crafts reaction. Would this reaction work as drawn? It would not. Exactly right. Remember, the Friedel-Crafts reaction does not occur. It does not occur when you have a deactivated aromatic ring. So you essentially see no reaction take place. Remember, Friedel-Crafts alkylation and acylation does not occur when you have a deactivated aromatic ring. Does this example make sense? Okay, so let's keep going then. In this case, we're asked to predict the product from the following reaction. So looking at our substituents, we have a pi donor, which is an orthodirector, and we have a sigma donor, which is an orthodirector, but a weaker orthodirector. So the stronger directing group wins out in terms of the major product for this reaction. It also helps that this T-butyl group is so bulky, we are not going to see significant reaction at the ortho positions relative to that T-butyl group. So in our first step, we need to generate our electrophile. So aluminum trichloride is going to facilitate the loss of chloride and ionization to make a carbocation. Now, my question to everyone then becomes, is this carbocation one of the more stable carbocations that we can generate? There's no rearrangement in this case, so we won't see a significant amount of carbocation shifts or other rearrangements. So with that established, we now have our electrophile. So let's bring in our aromatic ring and let's show how the aromatic ring will react with our electrophile. So our nucleophilic pi bond will attack our electrophilic carbocation. That in turn will generate a carbocation intermediate. And then from there, chloride or any remotely basic species will come in and pull off a proton. That in turn will generate and regenerate our aromatic system. So this is our major product. We don't typically see polyalkylation for these hindered substrates. If polyalkylation occurs, you would see substitution adjacent to the less hindered methoxy group, not only because it's a stronger directing group, but also because that minimizes hindrance. Though this product is very minor because you'd get this substitution pattern where you have your methoxy group in between two very bulky substituents, and that introduces a lot of steric strain. So this is one case where polyalkylation is minimized due to steric effects. Does that answer your question? Let me see. So when does polyalkylation occur to the major product? It occurs when your substrate is not particularly hindered. Polyalkylation is usually commonly observed for Friedel-Crafts alkylations. However, if the substrate is heavily sterically hindered, you don't see a ton of polyalkylation due to steric effects. Does that make sense? Okay, perfect. Any other questions on this example? Okay, so let's keep going and let's look at this next case. In this case, we have a hydroxy group, which is a pi donor. So an ortho-para director. And we have an amine, which is also a pi donor or an ortho-para director. Okay, so with that established, we would expect to see reaction at these three possible positions. So I'll label them A, B, and C. However, as we discussed in lecture, what position is not favored for a reaction? C, right? You typically don't see substitution in between substituents due to steric effects and steric strain. So as a result, we'd primarily see reactions at positions A and B. Okay, so let's showcase that reaction mechanism. So in this case, we attack our electrophilic bromine atom. We see substitution ortho relative to the amine. That also generates a carbocation. And then from there, an equivalent of bromide comes in and removes our proton. So we observe the ortho substitution product relative to the amine. And we also observe as an equally major product the para-substituted product relative to the amine. So these are our two major products. Does this make sense to everyone? Any questions on this example? They're both equally preferred. There's no strong preference for either substrate since the steric and electronic profile is almost identical. Perfect. Okay, let's look at this next substrate. So we have multiple electron withdrawing substituents, a halogen, and we're treating it with a nucleophile in the presence of heat. What mechanism are we going to observe in this case? E2 would not be observable if we have an sp2 carbon. The closest thing you can invoke is benzine, which does not work in this case when you have an electron withdrawing substituent. SN1 wouldn't work either because this position is sp2. So as we discussed in class, what happens when we have multiple electron withdrawing groups on an aromatic ring? We see SNAR, or nucleophilic aromatic substitution. This isn't just an academic curiosity, it has practical use in synthesis. So in SNAR, which occurs when we have multiple electron withdrawing groups, our nucleophile attacks the same carbon as our leaving group, and we generate a stabilized anion. And this is why we need electron withdrawing groups, because without these electron withdrawing groups, we would not be able to stabilize this negative charge efficiently. From there, we observe what amounts to almost a textbook E1CB-like mechanism where our electron pair kicks back down to regenerate our pi bond and kick out our leaving group. And the most important thing about this SNAR reaction is that it very selectively generates only a single product. Yes, the leaving group must be ortho or para to the electron withdrawing groups. Generally, if it's not ortho or para, you are not able to stabilize the negative charge. Benzine can be observed in those cases, but typically benzine is destabilized when you have withdrawing groups or donor groups. Benzine works best when you have relatively neutral substrates. Does that answer your question? If it's meta, you'd probably go through a benzine intermediate, but it wouldn't be very clean. Any other questions on this example? Okay, let's look at this next case. As we were talking about benzine, if we treat the following substrate with sodium ethoxide and heat, what mechanism will we observe? This time we don't have any electron withdrawing groups, so what will we observe? Yep. So we'd observe a benzine mechanism. So following the first step in a benzine mechanism, our base pulls off a proton, and that in turn kicks out our leaving group and generates benzine, which is a highly reactive intermediate. From there, a second equivalent of our nucleophile attacks benzine. It can attack from either position, as both positions in benzine can function as electrophiles. This generates a highly basic sp2 anion. Well, yeah, sp2 anion. And then that quickly pulls off a proton from solvent or another even remotely basic molecule to regenerate our product. We also observe the other regioisomer as another major product, and that this product is derived from attack at the other position. Does this example make sense to everyone? So you only observe two regioisomers for benzine. You can attack at either two positions on the benzine intermediate. So you would observe two products going through a benzine mechanism. Does that make sense? It doesn't matter the location of the other group. You'd only see two possible regioisomers. Does that make sense? Well, by definition, you can only have two regioisomers through a benzine mechanism. The only other case, one other thing that we can note, however, although this isn't entirely favored, is that you can just as easily eliminate from the opposite position. And in this case, depending on your substitution pattern, attack onto this benzine intermediate could yield different products. And that's probably what you're referring to in your question. Yes, by definition, you can make multiple different benzine intermediates, and as a result, you can end up with multiple regioisomers. That's not observed in this example, however. But if the chloride was meta, yes, you would see a mixture of regioisomers. Any other questions on this example? Any other questions that I can address? Okay, let's keep going. In this case, we're asked to provide an efficient synthesis of the following compound from benzene, phenol, aniline, or toluene. One of these substrates and starting materials is easier to start with than the other. So first thing to note, we have an alkyl group, which is an ortho-para-director. We have a bromine that's an ortho-para-director, and we have a 1-3 relationship. So the first thing I'm going to do, if I want to install this bromine, since we have to install this bromine, we don't have a choice in the matter. It seems easier to install this bromine in the meta position if we have a meta director, such as an acyl group. Okay. From there, we can trace back and install the bromine just via bromination. And what is a fast way to form a carbon-carbon bond shown here? What's a fast way to form a carbon-carbon bond between an aromatic ring and a carbonyl? What textbook reaction would work? Grignard would not, it's usable, workable, but it's not the most efficient. A faster method would be the Friedel-Crafts reaction. So we can trace this back to benzene and the following acyl chloride, which is readily prepared. Okay, so starting from benzene, we can treat it with this acyl chloride and aluminum trichloride, and that in turn generates our desired ketone. From there, we can brominate it, and that in turn generates our brominated product at the meta position, because this group is a meta director. Electron withdrawing groups direct substitution to the meta position. Finally, do we have an easy method to get rid of an aryl ketone? Do we have a method to convert aryl ketones to alkyl ketones? Yep, we can use hydrogen palladium, hydrogen platinum. You can also use the zinc mercury amalgam with hydrochloric acid, though I would prefer these first two options because they're least likely to go after your halide. Zinc mercury can sometimes get a little too reactive and burn off your halide as well. Does that make sense to everyone? Any questions on this synthesis example? So once you recognize the issue with regiochemistry, we can design a synthesis to prepare this molecule. This is just one solution. There are probably 5 viable routes using reactions that we've learned about in this class. And whatever route you use, as long as it addresses the chemoselectivity and regioselectivity concerns, it's perfectly reasonable. Any other questions on this example? Okay, so let's keep going then. So let's look at the following example. So we have the following synthetic scheme to prepare 2 unique products. In this case, these should be stereoisomeric products. We're asked to draw the product for each step in route A and route B with the correct stereochemistry, draw a Newman projection to justify our answer, draw a mechanism for each step in route A and B, Route 1A can be completed in a single step with a single step set of reagents. So list the reagents and conditions. Okay. And when T-butoxide is used in place of pyridine, an identical product is observed. Draw a structure for the product and show a mechanism. Okay. So let's start with route A. So let's start just by drawing out the mechanism for each step in route A. So we have the same stereochemistry for our starting material for route A and route B. So when we treat with toluene chloride, so I'm going to draw out the structure for toluene sulfonyl chloride. So our alcohol attacks toluene chloride, and that generates the tosylate derivative. We can pull off a proton with pyridine. The first time a functional group is mentioned that involves an abbreviation, I would ask that you draw out the full structure for that functional group before abbreviating. So you should clearly show me what a tosylate is, so that way I know that you know what the structure of a tosylate is. You can't draw a mechanism without the structure. Does that point make sense to everyone? Okay. One thing that's important, and this is a key subtlety that needs to be noted, is that when you make a tosylate, the tosylate is installed via reaction at the alcohol. As a result, the stereocenter is not changed when you generate the tosylate. And the configuration at the alcohol stereocenter is maintained. Does that point make sense to everyone? Okay, so we've drawn out the product from the first step. Now let's look at a Newman projection. So in this case, for our Newman projection, every group with a wedge will be on the right, dash will be on the left. So our methyl's pointing down, the tosylate's on the right, a proton's on the left, the isopropyl's pointing up, the cyclohexyl group is on the right, the hydrogen's on the left. I'm just going to redraw this Newman projection so that way our tosylate and the proton are more explicitly drawn anti-periplanar. Now, since we're treating a highly substituted alcohol with base, and we have a really activated leaving group, this is a textbook E2 reaction. So as such, we're going to need to set up our leaving group and our proton in an anti-periplanar arrangement. So from that arrangement, our base will pull off a proton and kick out our leaving group, and we generate the following alkene as a single stereoisomer. So this is the single product observed from route A. We discussed this example when we talked about the elimination of alcohols in a stereo-controlled manner via the E2 mechanism, and when we in our note section on the elimination of alcohols. Does this make sense to everyone?
I think you have too many hydrogens in your product.
Oh, yes, yeah, yeah. Let me check.
I got
Yeah,
the
one moment.
I got the isopropyl group across from the
Let's see, isopropyl, hydrogen. Ah, I see what happened. One moment. So to redraw it, we have the tosylate, hydrogen, methyl. We have the hydrogen, the cyclohexyl. Sorry about that. When I tried to move one of the lines to the front, it ended up staying in the back. Okay, perfect. So here's our redrawn structure. Yep, and then elimination with pyridine. Gives us the following alkene as a single stereoisomer. And that's based on the fact that our hydrogen and our leaving group must be anti-periplanar. So in this case, we isolate the Z alkene from route A. Does this make sense to everyone so far? Any questions so far? So let's look at route B now. So for route B, we have the same starting material. Exact same starting material. However, this time we're treating it with phosphorus tribromide, which is a relative of thionyl chloride. The reason why we moved away from thionyl chloride is depending on the substrate, thionyl chloride can do some weird reactions. So phosphorus tribromide is typically used if you want to install a halogen with inversion of stereochemistry. To showcase that, our alcohol will attack our electrophilic phosphorus atom. And then from there, our nucleophilic bromide ion will then attack and displace our alcohol. That in turn gives us the following alkyl bromide with inversion of stereochemistry. Does everyone see how the stereochemistry at our carbon stereocenter has been flipped because this is an SN2 reaction? Does everyone see that? Okay, so when we make a Newman projection, anything with a wedge is on the right, anything with a dash is on the left. So our methyl is pointing down, the isopropyl is pointing up, the cyclohexyl group is on the right, hydrogen's on the left. This is equivalent to our bromine pointing up, hydrogen on the right, methyl on the left, hydrogen pointing down, isopropyl on the left, cyclohexyl group on the right. Generally, the E2 reaction is stereospecific. So if you have the opposite configuration for the stereocenter containing your leaving group, you'll get the opposite alkene. So now that we have our hydrogen and leaving group set up in an anti-periplanar arrangement, we can eliminate our leaving group. And that in turn gives us the following product. And in this case, we isolate the E alkene from route B. If we compare to route A, does everyone see the difference? Does everyone see the difference between our two routes? How they give different alkene geometries? We talked about this in the chapter 16 and 17 note set. Any questions on this example? Okay, so let's keep going then. Now, you may be wondering, pyridine, that's a bit strange for an E2 reaction, right? Well, there's a reason for it, and a very good reason. So let's look at route A first. So you have this tosylate, you're wanting to set up a nice and effective E2 reaction, you break out the T-butoxide. Would anyone like to share why is T-butoxide not a good idea for this substrate? What's special about T-butoxide? Sterics, right? You have these relatively unhindered protons, and T-butoxide is going to go straight for them. Yep. So as a result, your elimination still occurs via an E2 mechanism, but instead you get elimination to form the least hindered alkene. And what's really funny is both routes A and route B give the same product. And that's because when you have these hydrogens, on your methyl group, you can always find an anti-periplanar hydrogen. By definition, if you have a methyl group, there is going to be a hydrogen that's anti-periplanar to your leaving group. You can make a model if you want to prove that statement, but you will always be able to eliminate if you're eliminating from a methyl group. So when you have a bulky base, as we discussed, the E2 reaction prefers to generate the least hindered alkene because we're abstracting the least hindered proton. Now, the reason why I chose pyridine is it's a nice medium ground, and it's also a hint for how we can accomplish route A. Is there another set of reagents that we could use to accomplish route A? Yep, phosphorus oxychloride and pyridine is also useful for E2 conditions. And that was covered in the notes. Okay, so does everyone understand this example now? Does everyone see how you need to be really careful for E2 reactions at analyzing the stereochemistry of your reactants and your products? Does this example make sense? Does everyone see how, depending on whether you use a tosylate or whether you make the alkyl halide, you get different product stereochemistries, and as a result, as a consequence of that, the E2 reaction, which is stereospecific, gives different alkene products. This was all covered, and these pieces were covered along with some worked examples in the chapter 17 note set. Any other questions on this example? Yes, I can scroll up to A. Yeah. Perfect. Any other questions on this example? So as you notice, even though it looks complicated at first glance, we've actually covered all the pieces explicitly in examples in the note sets. Okay, let's move on to the next example. In this case, a nice thing about epoxides is they're wonderful starting materials for making derivatives because they can be resolved and isolated as a single enantiomer. So we're going to look at a synthetic sequence where we prepare two unique compounds through a sequence of epoxide opening and then oxidation. So we're asked to predict the product for each step of route A and route B and draw a mechanism. Okay, so in the first case, we're looking at route A. So we have the same epoxide. I really like these divergent syntheses problems because they're so instructive in terms of showcasing stereospecific reactions. No longer can people just put plus enantiomer and call it a day. They have to actually explicitly draw out every product. Okay, so what's going to happen when we treat an epoxide with a Grignard? So we have two sites, A and B. So epoxide opening under basic conditions, what side do we attack? What carbon do we attack? Carbon A or B? A, exactly right. Under basic conditions, we're dealing with a textbook SN2 reaction. So we open our epoxide with anti-Markovnikov anti-Markovnikov regiochemistry. And now this is important. This is really important. What is the stereochemistry of our installed alkyl group? If our alcohol's pointing down, is our Grignard syn or anti to the alcohol? Anti, yeah. R is not actually correct for the assignment for this stereo center. The center is S, just as a note. But yes, the nucleophiles installed from the opposite face relative to your epoxide. It's an anti-stereochemistry and an anti-Markovnikov regiochemistry. For our next step, when we quench with acid, I noted that it was a quench, so that way I didn't see students drawing an acylation reaction. You would get your opened tertiary alcohol. Notice, in this case, do I put plus enantiomer? Is it applicable to put plus enantiomer in this case? No, you start with a single product. This is a stereospecific. You start with one stereoisomer, you end with a product with defined stereochemistry. Does that make sense? Okay, so let's look at a polar opposite case, where in this case we have an epoxide. We treat it with H3O plus and N-propyl alcohol. So what's going to happen here? What's the first step in this epoxide opening under acidic conditions? What's going to happen first? What's the first thing that's going to happen? We're going to activate the epoxide oxygen. How? How are we going to activate it? Via protonation. Yep. So we're going to protonate our epoxide. That makes an activated intermediate. We now have a much better quote unquote leaving group. And now what's going to happen next? So we have our nucleophile. What carbon is it going to attack? A or B?
B.
B. Epoxide opening under acidic conditions, we attack the more substituted position. It follows Markovnikov regio control. And this is pretty cool because now, just like before, what is the stereochemistry of our installed alcohol? Is it syn or anti? This installed alkoxy group, will it be syn or anti? Anti, so it's pointing up. That's important. Markovnikov regio control, anti-stereochemistry. From here, all we have to do is deprotonate our alcohol, and that gives us this first intermediate. Now, this may be a somewhat obvious question, but it's important to state premises so that way we can have a full discussion. Why do we only show Des-Martin Parietaine treatment for one of these substrates? Would anyone like to explain why for route B? Route B is the only product that we treat with Des-Martin Parietaine. Yeah, you can only oxidize a primary or secondary alcohol. Here we have a tertiary alcohol, and no matter how hard you try, Des-Martin Parietaine will not do anything to that tertiary alcohol. There has to be a hydride equivalent, barring like a permanganate oxidation or something really forcing. Does that make sense to everyone? You can, by definition, only oxidize an alcohol with Des-Martin Parietaine if it's primary or secondary. If you don't have a hydride equivalent, nothing will happen. Okay, so while we're on the note of acidic and basic conditions, before we finish out this Des-Martin Parietaine mechanism, let's answer the question posed. A chemist wanted to prepare the following compound using route B and the following nucleophile. Would this reaction give the desired product? So we are treating this epoxide with acid and cyanide. Would this reaction work as drawn? Would this reaction work as drawn? It's a simple reaction, right? You're making just a tertiary nitrile, right? Looks easy, looks very straightforward. Everyone's saying no. Would anyone like to explain why? Would anyone like to offer an explanation for why? So we're making hydrogen cyanide, right? And is hydrogen cyanide a good nucleophile? Not really. It's sort of a bad nucleophile. If anything, it's more reactive at nitrogen. So it's important, and this is a really important idea, your nucleophile needs to be compatible with acidic conditions. So under acidic conditions, which you want attack at the more substituted position, you need to have a nucleophile that can actually accommodate those acidic conditions. Hydrogen cyanide gets protonated and then it's sort of useless as a nucleophile. These conditions are just a fast way to make hydrogen cyanide gas rather than actually get any productive reaction going. Does that idea make sense to everyone? Any remotely basic nucleophile. I mean, obviously you can't use a Grignard under acidic conditions, right? The same way that an amine would also be pretty bad under acidic conditions, right? Because you'd make the ammonium salt. Nitriles, also probably not a good idea. Any organolithium species is probably ill-advised under acidic conditions. Essentially anything that's remotely basic that can get protonated is not viable. You don't even, a weaker acid wouldn't even work, because if you have a weaker acid, then you'd see more of the nucleophilic SN2-like pathway. So if you run it just using cyanide, then cyanide is going to attack the least substituted position, and we'd make the following product. Whoops, let me draw the cyanide with a 180-degree bond angle. So if we're under nucleophilic conditions, we get the wrong regioisomer. If we're under acidic conditions, nothing happens. In fact, if anything, what you would see when you protonate your epoxide, you wouldn't get the cyanide, you wouldn't get the nitrile. Instead, you'd get something that's very, very noticeable, and you'd likely want to leave the room because this thing was going to smell terrible. You'd get the isonitrile, because when protonated, the isonitrile is actually reactive at nitrogen. So instead, you're going to get this nasty isonitrile, which are infamous for their terrible smell. Thankfully, this one's not too volatile, but nonetheless, it's not exactly something you want to be generating. So there's actually been a lot of work to prepare these tertiary nitriles with stereo control and regio control. It's a trickier synthetic problem than it lets on, and often has been accomplished via multi-step routes. Even then, I'd like you to note that this nucleophilic attack is not particularly favored, and you'd primarily see a lot of elimination. So generally, if you have an ineffective nucleophile under acidic conditions, then it's difficult to open up an epoxide. Yes, we're going to show the next step for Dess-Martin Parietane oxidation in a moment. So does this point for this question part make sense? Does this part make sense to everyone? Okay, so let's now show the Dess-Martin Parietane oxidation. So we have our secondary alcohol, and we treat with Dess-Martin Parietane. Remember, Dess-Martin Parietane looks like this. It's an iodine 5 reagent. Our alcohol attacks, kicks out our leaving group. Now, from here, what we're going to do is we're going to pull off a proton. That in turn generates the following intermediate. From here, we'll be able to pull off a proton, form a bond between our carbon and oxygen, form our carbonyl, and then from there, that reduces our iodine from iodine 5 to iodine 3. This is a concerted mechanism, and in the end, I'm just abbreviating these side groups. It gets a little congested around the site of reactivity. So I'm just abbreviating our other groups as OR. The iodine's actually not doing a ton, but it's just serving as an oxidizing agent. So in the end, we get this highly alpha substituted ketone. And it's pretty difficult actually to prepare these substrates under normal conditions. Does this make sense? Yep, we get a single product because the oxidation, we're only reacting at our alcohol position. So the other stereocenters don't get modified in any way. So this is a useful method to prepare highly substituted ketones with both stereo control and regio control. Does this example make sense? Again, even though it looks complicated at first glance, all of the pieces we've actually covered, and in fact, everyone in this class has drawn a mechanism for each of these individual steps as part of our lecture discussions. So, any other last minute questions on this example? Okay, so let's look at the next case. In this case, we're asked to name the following compounds. So would anyone like to propose a name for compound A?
I do.
Sure. Yeah.
1S, 2R,
Yeah.
4S,
Okay.
2 tert butyl,
Okay.
4 iodo,
4 iodo,
cyclopentan, 1 all.
cyclopentan, 1 all. Okay, so dissecting the student response, they use the following numbering scheme. The alcohol's highest priority, so it gets priority number 1. Butyl. Now, in order to assign locant numbers, we want the lowest possible locant number. So assigning 1, 2 rather than 1, 3. 2 is less than 3, so we use the numbering method shown here. Does that make sense to everyone? Locant numbers are assigned to give the highest priority group the lowest locant number and the lowest overall set of locant numbers. So 1, 2, 4 is exactly correct. Butyl goes before iodo, B before I. Yep, perfect. Okay, now let's look at stereochemistry. Okay. Okay, so I'm going to draw the priority numbers in red. The oxygen's priority 1, substituted group is priority 2, unsubstituted group is priority 3. So tracing this first center would be S. For the iodine, iodine's priority 1, the group with the alcohols priority 2, the other group's priority 3. So tracing, that gives us an S stereocenter. For our last stereocenter, I'm going to draw out not the mirror image, this is the rotated structure. Okay, and from here, in terms of priority, this group with the alcohols, priority 1, the T-butyl group's priority 2, the normal alkyl group is priority 3. So tracing, that gives us a configuration of R. So we have 1S, 2R, 4S. Yep, this full name is completely correct. Any questions on this example? One thing I would note is that make sure you're using the naming conventions mentioned in the class and the rules that we mentioned in the class. Computer programs can name some of these compounds using IUPAC nomenclature methods that were not taught yet. So when you get to some variations, if a computer spits out a slightly different name, it may be using a valid IUPAC naming convention, but different from the rules that were discussed in class, since there are multiple variants of IUPAC rules for different compounds. And whether you're dealing with the formal name or informal name, or of course, like with epoxides and with aromatic systems, there are some variants on what reasonable IUPAC names you can name for different compounds. So make sure you're naming using the conventions discussed in the book and the class. Because if I see another name, it obviously looks a little bit weird, you know. Does that make sense to everyone? So let's look at this next structure. Let's look at naming compound B. Oh, wow. Students are pretty fast at this. Okay, we have two proposed names of 2R, 3S, 4Z. Oh, that's interesting. 4-methyl hex 4-ene 2,3-diol. Okay, so the following numbering convention was used to minimize the locate number for our alcohols. We have an alkene. Our two highest priority groups are on the same side, so we have a Z alkene. The stereochemistry for our alcohols, let's look at the locate numbers and the priority numbers. The alcohols, priority 1, the other alkyl chain with an alcohol is priority 2, the alkyl group's priority 3. So that gives us an R stereocenter. Drawing the reflected, drawing the rotated structure, we can now assign the stereochemistry at the other center. So looking in terms of priority 1, 2, 3. So our second center looks to me like an S stereocenter. So 2R, 3S, 4Z. Those all look correct. We have a methyl at the 4 position, hex because we have 6 carbons, 4-ene because the alkene's at the 4 position, 2,3-diol because we have 2 alcohols at the 2 and 3 position. Yep, this name looks completely correct. Any questions on this example? Did my explanation provide insight into why this answer is correct? Does it make sense to everyone? Any questions before we move to the next example? Okay, let's look at structures C and D, and let's try to come up with a reasonable name for these structures. And I would try not to, well, you can name this as 3-chloro 5-propan 2-il aniline. So in this case, we're naming this compound using aniline as our parent aromatic ring. Chloro is first alphabetically. So because chloro is first alphabetically, we'd give chloro or chlorine the lowest locate number in the event of a tie. This 5-propan 2-il, that's technically correct, but that's very similar to what computers would do for naming this compound. Probably the more common name would be 3-chloro 5-isopropyl aniline. The first name isn't wrong, but it's very computer-like. Does that make sense? Like propan 2-il, it's correct, but it's often not what, when someone's naming something, they often call propan 2-il isopropyl. This method of naming is correct when you have complicated side chains, but generally it's easier just to name these complex but well-defined side chains using their IUPAC name. Does this question make sense? Okay, now let's try to name structure D and try to name it like using the rules that we've discussed in this class. So the students all quickly identified, we haven't learned how to name carboxylic acids yet, so let's name this using the benzoic acid main chain. That's exactly what I want to see. And so we're using the following numbering conventions. Bromo goes before isopropyl because B is first alphabetically. So this would be named as 2-bromo 4-methyl 6-isopropyl benzoic acid. Okay, good. I was worried I was going to get the weird computer name for this compound that names it as a benzene derivative. Okay, so the reason why I'm discussing this is that computers are useful tools to help check your work. However, for the purposes of the exam and when you receive the exam, you won't be able to use those structure naming tools. And some of the problems are designed in a way where I'm expecting you to name these compounds using the class conventions. Okay? Does that point make sense to everyone? If I see computer names for many of these compounds, I won't accept them because we haven't talked about those rules yet. Okay, so now we're asked to predict the products. Keep in mind that these alkenes have stereochemistry, so you need to be cognizant of that when drawing out your mechanisms and drawing out your products. So the first step, we're looking at a hydroboration reaction, and the boron in borane will add to the least hindered or least substituted carbon, and the boron and hydrogen are installed with a syn stereochemistry. In turn, what that means is upon treatment with hydrogen peroxide and sodium hydroxide, an alkyl shift occurs and we install our desired alcohol. Do we put plus enantiomer in this case? Yes, because we can have approaches from either the top or bottom face. Does this make sense for this first example? We talked about this method to prepare alcohols. Remember, hydroboration follows anti-Markovnikov regiochemistry and syn stereochemistry. It would be easier to put plus ent enantiomer. You don't have to show the enantiomer as long as this plus enantiomer explanation is comprehensive. Just to illuminate what the enantiomer looks like, just to be explicit in this, it would look like this. Does that answer the question in the chat? Okay, let's look at this next case. We're treating an alkene with osmium tetroxide. What does that do? What are these textbook conditions for? Syn dihydroxylation, exactly right. So in this case, at the end of our first step, we're going to make the osmate ester. Now, from here, after treatment with sodium hydrogen sulfite, we cleave our osmate ester. And that generates our diol as well as the enantiomer. I'll just draw out the enantiomer just for your reference. Recall that many of these reactions were covered in the chapter 17 note set. Does this example make sense to everyone? Okay, so let's look at this next case. In this case, we're treating an alkene with bromine. So what does this do? It's dibromination, exactly right. So in our first step, we're going to make our bromonium ion. That in turn let's just arbitrarily assign this bromonium ion on the top face. And then when we draw out our mechanism, this is important. Which carbon is attacked, carbon A or B, when we open our bromonium ion? Do we attack with Markovnikov or anti-Markovnikov regioselectivity? We attack with Markovnikov regioselectivity. So bromination, we actually open the bromonium at the most substituted carbon with Markovnikov regio control and anti-stereo control. However, we also make the enantiomer, and the enantiomer covers the enantiomer covers this idea. Well, even though they're both substituted to the same extent, the reason why I ask you to draw a mechanism is that I want to see that you understand the mechanism for this bromination, right? So even though the enantiomer can account for if you predict the wrong regiochemistry, that doesn't mean that your mechanism shouldn't accurately reflect the regiochemistry of this reaction. Does that answer your question? Does everyone get the point? Yes, technically you can arrive at both of these products through Markovnikov addition. And I'm looking that you're showing the mechanism as going through a Markovnikov addition with anti-stereochemistry, because that's part of the entire point of this question. Because dibromination often masks. Yeah, if locant B had an extra methyl, then it would solely be B. That's correct. You already will see a preference for attack at position B anyways, because B is adjacent to a bulkier group and can experience greater stabilization from like hyperconjugation effects. No worries, that's why I'm answering the question. Any other questions on this example? Okay, so let's keep going now. And let's look at the following case where we treat an alcohol and an alkene with bromine. So this is a classic example of intramolecular ether synthesis. So for the first step in this reaction, we make a bromonium ion. From there, the bromonium ion that I'm going to arbitrarily draw on the top face From there, we have an internal nucleophile just all set and ready to go. And it's going to open our bromonium ion at the most substituted position. And that in turn generates our alkyl halide. And what's important to note is that is this ether installed with a dash or wedge? Is this ether on the top or bottom face? If the bromonium's on the top, where's the ether installed? On the bottom, exactly right. And then from there, as a cleanup step, water or another equivalent of alcohol will just pull off our proton. So this is an intramolecular variant of the mechanism that we discussed in class for ether synthesis. We also make the enantiomer. Does this mechanism make sense to everyone? So this is a textbook bromoetherification. Any questions on this example?
Would the oxygen carbon bond still be dashed?
Yes, yeah. It's implied by the drawing for the methyl, but yes, you can explicitly draw it as dashed.
Okay, cool. Thanks.
Any other questions on this example? Okay, let's keep going to the next example. In this case, we have an ester reacting with a Grignard. So as we know, esters react with two equivalents of Grignard to yield highly substituted tertiary alcohols. So in our first step, our Grignard will attack our ester and break our carbon-oxygen double bond. From there, we have this tetrahedral intermediate that can then collapse and kick out a leaving group of alkoxide. And you're certainly not going to kick out an equivalent of isopropyl anion, right? Carbon leaving groups generally are not very good leaving groups. We now have this intermediate ketone, but this intermediate ketone is never going to stick around. You're not going to be able to isolate it typically. It will instead get attacked with a second equivalent of Grignard, and that generates the following alkoxide ion, which then, when we quench with water, will give us our desired tertiary alcohol. Do we have to put plus enantiomer in this case? Is there any stereochemical information to be had? No, exactly right. So make sure you're deliberate when indicating whether or not you generate a mixture of enantiomers. Okay, let's look at this last example. We're treating a primary alcohol with chromium 6 oxide under acidic conditions. These are textbook exhaustive oxidation conditions. So in our first step, our nucleophilic oxygen atom is going to attack our electrophilic chromium atom. We're then going to have a series of proton transfers. From there, we now have our alcohol set up. We have our available hydride equivalent, and now water is going to pull off a hydride equivalent to yield an aldehyde and reduced chromium species. Okay, so from there now, a second equivalent of water is now going to come in and attack our aldehyde. This aldehyde is not isolable under the reaction conditions. It quickly gets attacked. We then have another set of proton transfers. And there gives us our desired diol. From there, we can attack another equivalent of chromium 6 oxide. And this is a repetition of the earlier mechanism. We have another proton transfer. That in turn gives us our alcohol set up and ready to go. And then water is going to pull off a second hydride equivalent. And we're going to kick our electrons to chromium. And that gives us our desired carboxylic acid. Does this example make sense to everyone? Any questions on this example? Sure. Any questions I can address? Any questions that I can address? Okay, perfect. Let's look at this next example. We have a classic sodium borohydride reduction. So in this case, our hydride equivalent will attack our electrophilic carbonyl carbon. And that in turn generates a secondary alcohol. No stereochemistry needed in this case. From this alkoxide intermediate, an equivalent of methanol will serve to protonate the alkoxide intermediate, generating our isolable secondary alcohol. Why am I not drawing stereochemistry in this case? Why am I not drawing stereochemistry? There's no stereocenter, right? The molecule is symmetrical. Does that answer your question? Any questions on this example? Okay, let's look at this next case. In this case, we're looking at a variant of oxymercuration, aminomercuration. Nothing that we haven't seen before mechanistically. The first step for this mercuration reaction is we have mercury acetate, and we coordinate our mercury to the alkene to make a mercurinium ion. I'm just arbitrarily going to draw the mercurinium ion on the bottom face. In our next step, and this is a really important idea, our amine is going to attack what carbon, A or B? Does oxymercuration follow Markovnikov or anti-Markovnikov selectivity? It follows Markovnikov regioselectivity. So we're going to attack and open up this mercurinium ion. And this is important. Does oxymercuration occur with syn or anti-stereochemistry? Anti, exactly right. So the amine is installed on the opposite face relative to the mercurinium ion. So in this case, we do end up with two enantiomeric products from the first step. This is an odd quirk of oxymercuration in that we end up with enantiomeric alkyl mercury species. So we have this plus the enantiomer. However, after sodium borohydride reduction, we end up with the following product. Do I put plus enantiomer in this case? No. Does this product have any stereochemical information at all? No. Right. This would best be drawn more appropriately just using the normal flat line method. Because this center isn't a stereocenter, it's symmetrical. So you go from a mixture of enantiomeric mercurinium ions to just an achiral product. Does that make sense? Any other questions on this example? Okay. So we're almost at the end. We're now asked to propose an efficient synthesis of the following compound from compounds containing 7 non-hydrogen atoms or less. Well, this aldehyde is going to be a bit of a pain to install. So what we're going to do is we're going to trace back this aldehyde to a vinyl group. You can also trace it back to an alcohol. I'm just showing one method. There are many methods that would work. From here, we can trace this back to a Grignard addition. However, one thing that I do want us to note is that if we're doing a reaction with a Grignard reagent and we have these alcohol functionalities floating around, what would we need to do to these alcohols? Protect them, right? So we'll trace back to the trimethylsilyl alcohols. And of course, we can trace back this set of alcohols to an epoxide. We can trace back the epoxide to the alkene. Okay, so in a forward sense, we can take this alkene, we treat it with MCPBA. That generates our epoxide. From there, we can treat it with H3O plus, or you can, H3O plus and water. That generates our anti-arrangement. Then we protect these alcohols with trimethylsilyl chloride and pyridine. That generates our protected diol. And then from there, once we have our protected diol, now, of course, you can use another Grignard. There are many solutions here, but I'm going to go with what I felt was the most intuitive and add this allyl Grignard followed by H3O plus. That in turn generates my alcohol while deprotecting my trimethylsilyl groups. And then from there, to get the aldehyde, all I do is treat with ozone and dimethyl sulfide. There are a ton of possible solutions for this problem. I just picked probably what I felt was the most straightforward solution. Does this example make sense? The key point in this problem is one, you need to make a trans diol, so you can't use osmium. The second point, which is equally important, is that you need to protect your alcohols if you're doing Grignard chemistry. If you forget the protection step, this reaction won't work. And for those who say, why can't we carry through the alkene? You'd run into chemoselectivity issues because you'd have two alkenes and the alkenes would both react and you wouldn't be able to get the desired product. Does that make sense? Okay, so we have one more synthesis to propose. This time you're proposing a synthesis from these two starting materials. Okay, again, there are a range of routes, but one thing I notice is that I can break this bond, and this looks to me like a nucleophilic epoxide opening reaction. So we can trace this back to the epoxide and this amine. Now from here, we can make the epoxide quite easily just via epoxidation of our alkene, right? So that's done. Now to make the amine from this alcohol, this looks like a double inversion process. We can make the amine from this defined alkyl halide, and then we can make this alkyl halide from our alcohol. Notice that we'd have to choose our conditions carefully so we have a sequential set of SN2 reactions. Remember this idea of double inversion by going through the alkyl halide? So in a forward sense, we take our alcohol, we treat it first with phosphorus tribromide. That in turn would generate the following alkyl halide. We then treat with ammonia. That in turn generates our desired amine. Our alkene we can treat with MCPBA. That in turn gives us our epoxide. And then we treat this amine with our epoxide. Do we need to use acidic, basic, or neutral conditions? Do I need any additives for this reaction? Basic conditions, right? Because we want an SN2 reaction. We actually wouldn't be able to get this reaction to go under acidic conditions. Remember, because the amine would get protonated and then the reaction would be dead in the water. Okay, so that gives us our desired product. Yeah, you can certainly use potassium carbonate. Non-nucleophilic base, that's more than okay. Any other questions on this example?
When we attack our like our base with the epoxide, would it change the stereochemistry at all, or no?
No, because the reaction occurs at the nitrogen atom, not the carbon center.
Oh yeah, okay. Thanks.
Does that make sense?
Yeah, I just was having a brain fart.
No worries. Okay, so we finished going over every question on the practice exam. Any questions that I can address before we archive this recording? So we'll archive this recording.